Assalamu alaikum wa rahmatullahi wa barakatuh. Hello, Dr. Fauzi. This is Uthman Al Hadiri, and today we are going to present our project about software packages and tools that have been used in recent researches in the field of high performance and parallel computing. So this is the table of contents of our presentation. We will start with the introduction, and then I will introduce my friends and team members. After that, we will talk about the literature review of the software packages and tools that we are going to talk about in this presentation, followed by a discussion about those tools and packages. Finally, we will have the references and conclusion. So this is our team. We have Abdullah Al-Sulaiman, Imad Al-Hadiri, and myself, Uthman Al-Hadiri. So in the literature review session, we will first talk about the general concept of high performance and parallel computing, followed by an overview of the tools and software packages that have been used in recent researches. So before we go deep into literature review, we need to take a look at the main software packages and tools in the field of HPPC. So let's start with the libraries. Libraries include the data configuration and documentation, and they are widely used in HPPC. After that, we have the compilers, which perform error checking and some other abilities. And most vendors of parallel systems supply compilers for parallel dialects of C and Fortran, and sometimes they are integrated with analyzers as well. However, the input of the compiler can be either a sequential or parallel program. And then we have the program restructures and parallelizers. These tools convert the sequential or the partially parallel program into a fully or efficient parallel program. These parallelizers or these tools convert this, transform the source code into another source code, not an object code, which is the case in the compilers. After that, we have the program specification and constructions. Also, we have the static analyzers, which are tools that analyze the program without actually executing it. Then we have parallel debuggers, and finally execution and performance analysis. So let's start our literature review by talking about the general concept of the parallel computing. The main goal of parallel computing is to cut the program into small chunks or parts. Now, why do we do that? We do that to allow these parts or these chunks to execute simultaneously at the same time, and therefore we can perform several tasks simultaneously as well. It also provides us with the opportunity to process or operate on a large part of or a large amount of data. So, for example, if we have like very large data, like thousands of terabytes, for example, and we need to perform a specific process on each of these data. Instead of performing it one data at a time, when we have parallel computing or parallel processing, we can perform these tasks like faster simultaneously, like perform on several data or many data at the same time, many let's say gigabytes or few gigabytes at a time, and also we can make by doing this we maximize the utilization of our processors that are in our computers or the operating computers.
All right. So moving after what my friends were saying about the overview of the high performance parallel computing, we realized that our main goal in parallel computing is to achieve a program where the execution of that program is utilizing all the resources that we're having. And basically, this is what I'm going to be talking about now, which are the software tools that helps you achieve this kind of utilization for the resources, and that helps you to understand how your parallel program is performing in order to let you be able to modify it and identify the weaknesses, and lets you exploit the concurrency of the task and of the computations. Because as much as you can understand this from the scratch, you need to have an automation of these tools to help you be able to understand that. So starting with the parallel debuggers, basically they're extending the functionality of a normal debugger. A normal debugger like the GNU project, the GNU debugger, GDB, which is an open source debugger. It is always used to understand how a serial program is working during the runtime. When the program runs, it has its own variables in the stack, in the RAM, and even the registers of the CPU are being used to execute the instructions of that program. So for you as a developer, you need to understand how this program is working, how it is behaving. Uh, Probably this is a famous aspect for people who are doing malware analysis. You need to understand how such an executable file is behaving in order for them to understand how does it work. And the same thing excuse me. And the same thing happens with the parallel debuggers, is that they are made to let you trace or understand how your parallel program is behaving during the runtime. So you can view the registers, you can have it working for you to understand how a race condition is happening. Because when you're having a multi-threaded program, basically there's going to be a lot of processes trying to access the same resource at the same time, and there could be a race condition happening, and probably it will be giving you errors, and it will be hard for you to find them. And this is where the parallel debuggers hub or come into place, because they would allow you to set your breakpoints and understand how uh, how this race condition happened. And an example of these debuggers, of course, the Aram. Aram is one of the biggest companies in processors and microprocessors production. They have a DD debugger, which is Aram Alina Studio. Basically, their debugger is cross-platform. It allows you to have a memory debugging. It allows you to visualize a large amount of data. This is how they're advertising it, of course. And the amazing part of it is that it is supporting multiple compilers and multiple performance libraries. So this is one of the debuggers that are in the market. The other debugger that we have seen is the Timinagio. So Timinagio is basically a graphical solution for the parallel debuggers. It allows you to understand how your processes are interacting with each other, and where does the race condition happen, or the problems during the runtime. Going to the other tools that you need to understand, we need to talk about the program specifications and constructions. So when you want to perform a parallel program, or to achieve a parallel program, there is something called the HINTS, which is the heterogeneous network computing environment. So basically, having your multiple computers running on or having a network of computers to achieve a parallel task is a great option. It would give you a very high speed up, and it will allow you to execute or solve complex problems using the advantage of parallel computing. However, since you are running on a network of devices, a network of computers, you are basically having multiple OSs running on these computers. For example, you will have devices that are running Linux, devices that are running Windows. So this difference in the OSs would make it very hard for a programmer to do. And this is where the people who created HINTS in the first place were thinking about it, is that when you're having a heterogeneous network of devices, you need to have an environment that makes it easy for a programmer to build his program. So The philosophy is basically to have the programmer graphically specify the parallelism of the computers, of the computation that he wants to do, and then this environment is going to try to automate as much as possible of the coding and the construction of that program. And this is why it is good to have a software tool that allows you to specify your program specifications and how it's going to be constructed, so it can help you. And these are the pictures of how this Hints program works. This is the Hints tool from the study, and we can see that it can help you to visualize and compose the parallel computation of your program. Going to the third tool, which is the execution and performance analyzers. Basically, as we have mentioned, the debugging is very good when you are executing your program at the runtime. However, sometimes you would like to understand how your program is performing overall. So after your program has performed, you want to have a report of how did it work, what were the delays that were happening in this program, and this is where the execution and performance analyzers come, and this is where they happen, is they are they determine where the bottlenecks that could happen. And an example of these tools is the XPVM, which is a performance analyzer for the PVM platform. This is how the tool, it provides you a graphical interface for the PVM console commands and information, along with several animated views. These animated views are going to help you identify where does the bottlenecks happen, where are the delays that are making your program not executing as it is supposed to be. So these are one of the good tools for you to have during your work to achieve a parallel task. So as you can see, this is how does the report looks.
So let's start with the literature review of the software packages. Software packages actually are pre-written programs that have been developed to fit the activities in parallel computing. So the main software packages in parallel computing, or some of the main ones, are CUDA, OpenCL, OpenACC, MPI, and OpenMP. And we are going to talk about the first three in this presentation. So Compute Unified Device Architecture, or CUDA, was developed in 2006 by NVIDIA. It gives the programmers the opportunity to access GPU so that it can be used for parallel computing. It also includes some functions that allows the transformation or the shifting of data between CPU and GPU. And in recent versions of CUDA, a few functions or methods have been included to communicate directly with multiple GPU accelerators. So CUDA is designed to develop applications scaling transparently. It also gives the researchers or the programmers the opportunity to use C as a high-level programming language. And for CUDA, the parallel system consists of the host, which is in this case the CPU, and a computation device or resource, which is in this case the GPU. And as we can see here in the figure, we have the host, which is the CPU, and the global memory as our GPU, and we have two parallel threads going simultaneously. Each thread has its own local memory and private memory and work item as well. So the computations tasks are done in the GPU using a set of parallel threads, as we can see here, and also the structure or the architecture of the GPU threads are represented in two-level hierarchy, which consists of block and grid, as we can see here in the figure.
Assalamu alaikum and good afternoon. My name is Imad Al-Hudiri. So in this section, I will go through the rest of the software packages that we have reviewed. Those software packages were used in recent researches in high performance and parallel computing. So I will start with OpenCL or Open Computing Language. OpenCL basically is a framework for writing programs. And it executes across heterogeneous architecture. So what I mean by heterogeneous is we are running at two different architecture at the same time, as such CPU and GPU. So OpenCL is basically a library that can be used with any C or C++ compiler. OpenCL programs are compiled into kernels. So, and those kernels are written separately in C-like language. And those kernels are compiled at runtime for the present hardware. So as a continuation of the OpenCL, so OpenCL programs are divided into host and kernels and kernel code. So only the kernel is executed on the compute device. So if we look at this on the figure on the right, which represent the OpenCL execution model, so the OpenCL program or application is compiled into kernels, which can be applied to data. So the resulting data can be passed to the next kernel that requires it. So if any kernel requires the data, the kernel can possess it or can obtain it. So if we have a multi-core system, so that multi-core system can run multiple kernels at the same time. So the kernels could be the same. I mean, they could use the same kernel. So all cores use the same kernel. The cores could use different kernels, as shown in this example. The code, the application is compiled into 3 different kernels, and each kernel is responsible for part of the data. So moving on to the next program standard or software package, that is OpenACC, or we can simply say Open Accelerators. So it's a programming standard that's developed by Cray in 2012 for parallel computing. So OpenACC is also based on heterogeneous architecture. It targeted both the CPU and the GPU architectures, and it can launch computational code on both architecture, whether it's CPU or the GPU. So code fragments that require less computation could be done on the CPU, while fragments of code that requires high data computation and parallel data execution could be carried out on the GPU. So the OpenACC programming standard or API adopts a host-directed execution model in which the main program runs on the host, and the functions that requires an intensive computation and data parallelism are offloaded to an attached accelerator, or we can simply say the GPU. And the main memory model is based on separate host and device memories which don't synchronize. In fact, GPU devices implement a weak memory model that prevents coherence among operations on different or separate units, and allows coherence operation on the same compute unit only by using explicit synchronization. So we have to explicitly declare the synchronization. In this figure, this figure represents the OpenACC execution model. It's based on heterogeneous architecture. What I mean by heterogeneous is that we are running at two different architecture at the same time. So in this model, the program execution will start off running at the CPU, and work through the sequential parts of the code. But at the same time, when we hit a function that have a lot of work to do, and that we are going to offload that part of the computation to the GPU. So the GPU is going to work on the data parallel, parallel data computation, and then when it's done, we move back to the CPU. So here's a summary of existing work or existing researches on high performance and parallel computing. So basically, we have reviewed several papers, and we obtained the research author, title, and the issue that they work on, along with the software packages that they use, tools used, advantages, and limitation of the research. So the first paper was on the topic, the OpenMBI implementation of NAS parallel benchmarks and its performance. And this research is carried out by Jin in 1999. It's quite old. So he worked on the issue examining the effectiveness or the efficiency of OpenMB directives for parallelizing the NAS parallel benchmarks. So he used OpenMBI as a software package, and he used C compiler as a tool. So the advantages or the gain of the research was it's simple to program with the incremental path to full parallelization, and shared memory model, no need for explicit data distribution. Limitations of the research, the main disadvantages of programming with compiler directives OpenMB is the implicit handling of global data layout, since it may create performance bottleneck and not be easily overcome. The second research paper was on the topic parallel computation of a dam break flow model using OpenACC application. This paper was conducted by Zhang in 2017. So he worked on the issue, the simulation of dam break flow routine process. The software package that he used is an OpenACC along with PGI and C compilers as the tools. Advantages, a great efficiency and high speed up rate due to the fact that they use OpenACC. So OpenACC provided great efficiency and a high speed up rate when doing parallel data computation, and data handling. The third research paper was on the topic digital image processing using parallel computing. The paper was published in 2017. So they worked on the issue is that they are using a graphics processing unit. They are using the GPU in big data processing in the context of digital image processing. Software package or the framework that they used is CUDA, and tools they used MATLAB toolkit. So what are the benefit or gain that the research of the research outcome is that they take the advantages of the massive parallel computing power of Nevada graphic card to do general purpose computation. And as for the limitation, they need different types of data to be tested. So they need to have a large or vast amount of data, different types of data. so that they test it against their algorithm. The fourth paper was on the topic implementation of motion estimation heterogeneous parallel computing. The paper was published in 2012. So they worked on the issue of parallel motion estimation algorithm, and they used OpenCL as a software package.
Finally, after the literature review that we have been through, we come to the fact that unfortunately the current tools, like the tools that we have mentioned, the frameworks, and even the software that we have been through, the industry for the research in high performance parallel computing is actually suffering from a limitation in these tools. These tools are considerably limited. This is due to the fact that firstly these tools are being developed within the labs of the universities. Like each university would develop the tool that helps them in their own research. But then when another university wants to choose it, they would find that these tools are kindly limited, as they were not made to be used by everyone. And the other thing is that the vendors in the market, they are not funding the development of these tools very well. We have good ideas for tools. Tools are currently considered to be prototypes, but if there was enough funding for this, then these tools would be very useful to the industry of research in high performance parallel computing. However, the vendors are not providing enough funds, and since there is no enough fundings for these tools, this means that they will be considerably limited as when it comes to what these tools can provide for you, and how could they help you in performing your research via the parallel computing paradigm. I think that's all for us. Thank you very much. And here is a list of the references that we have been using in our research. Thank you very much.